In this video, we're going to talk about two different ideas that go together: distance, velocity, and acceleration, as well as higher order derivatives. The two go hand in hand. So I have this graph. It has really no context. I don't have a story behind it other than we're tracking the position of something from the start. So we're measuring its distance from the start in feet and how much time has passed in minutes. So no real story behind it. What we're going to do is analyze what's happening. We can see that from 0 till about 3.5, the distance from the start is increasing. And then from 3.5 until 7.5, the distance decreases. Okay, so we can see that the graph is going up and then the graph is coming down. So we can describe what's happening in those words. The distance is getting larger, so we're getting further away from the start, and then the distance is getting smaller, we're getting closer back to the start again. So we have an increasing function until here. This function is increasing. We're getting further away from the start and then decreasing. What I want to talk about is the rate of change. So we've talked about rate of change as a derivative so far, and let's look at what the rate of change of this graph means. So if we look at the rate of change for this graph, if I find the change in y over the change in x, delta y, delta x, y2 minus y1 over x2 minus x1. If I look at the change in the y variable is feet, or measuring distance. And the x variable is measured in minutes, or it's measuring time. So if I look at how much an object's distance is changing, like its position, how much that position is changing over time, that gives me the velocity. Now, something to know about velocity, you've probably learned this in physics, but if you haven't taken physics yet, velocity is not only how fast something is going, so it's not only the speed of that object, but it's also the direction in which that object is traveling. So let's take a look at our graph up here, this purple graph, and we're going to look at the velocity on these different locations. So we're going to look at velocity. The velocity is slope. Let's look at tangent lines, because that's what we've been working with, is instantaneous velocity or instantaneous rates of change. So if I look at the slope, let's just draw a tangent line right here. I can see that the slope is positive there and relatively steep. As we continue along this curve, the slopes are still positive, however, the slopes are becoming less steep until I reach this point right here. So the interesting part is on the interval from 0 till, I'm going to put parentheses because we're going to use the open interval. At 0, nothing's happening, we haven't been moving at all, to about 3.5. I'm going to assume that the vertex is at 3.5. The distance from the start is increasing. We also see that the velocity, or the slope, the rate of change, is positive on this interval as well. So the rate of change, or the velocity, is positive. Okay, I'm going to use a different color for the decreasing so it'll make a little bit more sense. So if we talk about where we're getting closer to the start again, so the distance is starting to decrease. I can see that if I were to draw tangent lines here, I can see that all of those velocities, the rates of change, all have a negative slope. So let's talk about that. On the interval from 3.5 to 7.5, the distance from the start is decreasing. And also on that interval, from 3.5 to 7.5, the rate of change, or the velocity, is negative. So we can see that not only speed but direction. So when the velocity was positive, or when the distance was increasing, we were moving away from the starting point. So the positive velocity tells us we were moving away from the starting point. And then from 3.5 to 7.5, the distance started to decrease. And the velocity, or the rate of change, was negative because we were heading back toward the starting point. So what happens here at this point at the top? What is the velocity there? And what does that mean? So in this case, the velocity is 0 here at 3.5. That's the rate of change. There is no rate of change. The slope is 0. That's a flat spot. The velocity is 0 at time equals 3.5. The object turned around. Okay, so we had some things going on here. Let's see if we can wrap this up in a formal way, and then I'm going to give you a chance to practice. I'm going to use, let's see, what color? Let's use hot pink. So what we found out then is that the velocity equals the change in y over the change in x. And that's another way of just saying the slope. So we say that, I'm going to start at the beginning, if the position function is f of x, then the velocity is that slope, that rate of change, so that velocity would be f prime of x. And what we found so far is that if f prime of x is positive, the position is increasing. We're moving away from the start position. If f prime of x is negative, the position is decreasing. And if the velocity is 0, there is a change in direction. Okay, let's see if we can graph what this velocity function might look like. So I'm noticing that up until 3.5, the velocity is positive. Then at 3.5, the velocity is 0. And then after that, the velocity is negative. So let's graph that velocity function. Notice I'm going to use a completely new set of axes because we are going to have a different x and y value, or x and y axis. I'm going to move that over. I'm going to put it here. So the x-axis is still going to be time. Nothing is different there. This is still time in minutes, but the y-axis is measuring velocity. It's no longer measuring the position. So this is measuring the velocity. And in order to find the units for that, the units were change in distance over change in time. So in our case, the change in distance is in feet, and the change in time is in minutes. So the velocity is measured in feet per minute. .5 was a pretty key point, so I'm going to graph that here on my x-axis. We knew that before that the velocity was positive. After that the velocity is negative. And I'm just going to tell you, and we'll get to it in a minute, the velocity was positive, then we hit 0, then the velocity became negative. Right there, close. I'm going to make it 0. So this is the velocity function. Now let's think about what you know about derivatives. This was a parabola. This is an x squared something. So it's a quadratic. And you know that the derivative of a quadratic becomes linear. So it kind of makes sense that from the position function, the velocity would be a linear function. So the rate of change of the velocity is constant. What if we find the rate of change of the velocity? So what is that called? We said it was constant, but what is it going to be called? Some of you already know. You've taken physics. So let's look at the rate of change of velocity. So as the velocity is changing, how are we measuring that as time changes? So as velocity changes, so as your speed is changing, think about in your car. If you increase the speed, or if you decrease your speed, increasing the speed is acceleration. You're accelerating, you're speeding up. So when we talk about acceleration, acceleration is also like velocity. It's what's called a vector. It has a direction. So if I find, let's look at, we've got position is f of x, velocity is the change in distance over time, or change in position over time. That was the first derivative. And acceleration is the change in velocity over time. That's acceleration. That's the second derivative. Notice the two lines, that's double prime. F double prime is how we say that. That's the rate of change of the rate of change of the position. So how is velocity changing over time? If we look at this graph, the velocity graph, I'm going to try to think about what acceleration is. I can see here that if I look at the slopes of all of these graphs, or the slope on any point on this graph, the slope is negative no matter where I am. And the slope is exactly the same. So if I were to graph this acceleration function, new set of axes because I've got a new y-axis. This is time in minutes still. That part is not changing. It's still as time goes by. But now this is acceleration. And that's measured, it's feet per minute. So we're taking change in velocity, which is feet per minute, over minutes. So we can say it two ways. Feet per minute per minute. Those are the units. Or we can also say feet per minute squared. So I'll write this out here. So the acceleration is some negative value. We don't have the function, so we don't know exactly. I'm not labeling the y-axis, but here's the acceleration function. There's the acceleration function. We could also write that in feet per minute squared. That's how that's measured. Okay, the next video, you're going to practice this on a different scenario, and then we'll talk about how to write higher order derivatives.